A lot of times I'm asked the question, how do we know what to use as a factor, or how do we know that a particular number is going to work as a factor? Where do those numbers come from? And the answer to that is that we often use what's known as the rational roots theorem to find potential roots or possible zeros for a polynomial. It gives us a list of numbers that we can then investigate and with the hopes of finding a root to a polynomial equation. Now, the rational roots theorem says that possible rational roots exist at x equals the fraction p divided by q, where p is the list of all of the factors of the constant, and q is the list of all of the factors of our leading coefficient. So let's look at this example here. The constant value, or the number without an x associated with it, is the number 33. Now, we could use a negative 33 if we'd like. We could call it just a positive 33. It won't make a bit of difference when we use the rational roots theorem. Now, the leading coefficient is the number in front of x cubed, and in this case, that's equal to 1. So from this problem, or from this equation, I would say that p is equal to 33, and q is equal to 1. Now, our job would be to find the factors of p and all of the factors of q. So I'll do that down here. Find all the factors of 33, and I'll list them, and then find all of the factors of 1, and I will list them here. So when I think of the number 33, I know that 1 times 33 would equal 33, so that means that 1 and 3 both are factors. Factors mean that they divide the number 33. In addition to that, I know that 3 times 11 equals 33, and I think that's all of the numbers that would divide 33 evenly. Well, sort of. It's all of the numbers that would divide 33 evenly. What we can't forget is that both a positive 1 and a negative 1 would divide the number 33. And same thing with the number 3. You could divide 33 by a positive or negative 3, a positive negative 11, or a positive and negative 33. So really, instead of just 4 numbers that divide the number 33, there are 8. Both the positive and negative forms of each of these factors. Now for the number 1, this is really easy. The only number that divides 1 is 1, but we can't just leave it at that. We have to make sure that we indicate that both a positive 1 and a negative 1 can divide the number 1. So where do we go from here? Well, don't forget that the rational roots theorem says possible rational roots exist at p divided by q, where p is the list of all factors and of the constant, and q is the list of all factors of the leading coefficients. So our potential, and I have to stress the word potential here, all potential zeros occur at the result when I divide every factor of p by every factor of q. So with this list of numbers, I need to take every number in this list and divide it by every number in this list down here. And at times that can be quite difficult, but for this problem it's not too bad. I'm going to run through this list and think of what the result would be if I divide each of those numbers by each of these here. So let's first take these factors and divide them by the positive 1. Well, anything divided by 1 is itself, so if I took the positive 1 and divided it by this positive 1, my result would be 1. And if I took the negative 1 from this list and divided by the positive 1 here, well, I'd get a negative 1 as a result. So I know my possible zeros occur at positive and negative 1. Similarly, if I took the positive 3 from this list and divided by positive 1, I'd be left with a positive 3. And if I took the negative 3 from this list and divided by the positive 1, well, I'd be left with negative 3. And that's the same way that the positive and negative 11, as well as the positive and negative 33 would result in the rest of that division. Now, truthfully, we should be checking the next list as well. I'll take every number in this group and divide it now by -1, but an interesting thing occurs, and that's that we start doubling our responses, or we repeat our responses. If I had a +1 divided by a -1, well, I get a -1, and that's already in our list, so I'm not going to write that down again. If I had a -1 divided by another -1, well, that's a +1, and I already have that in my list. So that would happen for each of these other factors. I think we can stop here. This is a list of all of our potential zeros. And I think I can be a little bit more clear here because these are not only potential zeros, but potential rational zeros. There are other real zeros that could occur, but not at this location. So if this is a list of numbers that could produce a zero, we need to check to see if they are the numbers that will produce a zero. And the reason why we do that is because, well, this equation is only a cubic equation. There could be at most 3 zeros that occur from it. And so in that case, there could only be 3 of these zeros that, or 3 of these factors that do produce a zero, and we need to find them. And we know that one method that we can use to check for potential zeros is synthetic division. And in order to set up synthetic division, we need an L chart with one of our factors listed on the outside and all of the coefficients listed on the inside. So 1, -7, -41, and -33. And we can go through the synthetic division and look for the remainder that occurs here. If the remainder is 0, then we found a 0. But don't forget, there's another way that we can find our zeros now as well, and that's using the remainder theorem. All I need to do is put the factors or potential zeros into the polynomial itself and evaluate the polynomial. So if I evaluate the polynomial at 1, -1, 3, -3, 11, -11, 33, and -33, then I should find any of these rational results that equal 0. And if they equal 0, then that's an indicator that we have a root at that position. So let me show you how I would use the calculator to make quick work of these calculations. I have a calculator page open, but I'd also like to introduce a graphs page. So I'll click this drop-down menu and select to insert a graphs page. And here's where I'm going to name my function. And it'll be the same as the function that we have over here. So I'll write this as x cubed minus 7x squared minus 7x squared minus 41x minus 33. And I'll press enter. Now that I have the function stored into the calculator, I'm going to jump back to the calculator page. And from here, I will call upon the variable f, the function name, and insert each of my guesses or each of my estimates into this expression. So the first number I want to check is the number 1. The function evaluated at 1 is equal to -80. And so it doesn't equal 0. That tells me that we do not have a 0 at this location. I need to check the next one. So I will do the same thing, call upon the variable f, and evaluate this at -1. And now that one does equal a 0. So that's good for us. We found one of our zeros. Remember, there could be 3 of these in this list. So let's keep going until we find all 3 or until we run out of zeros. So the next one that I'll check is 3. Well, that equals negative 192. That didn't help us out. Now let's check negative 3. Ah, there's another 0. Good. We found 2 of them. Let's see if we can find a third. Let's evaluate at a positive 11. Ah, there it is. There is a 0 at 11. Now, it doesn't make a difference what these next ones are. We can stop right here since we found all 3 of our zeros. Now let's take a look back at the question, the way it was actually written. It says, find the real zeros of f and select the correct choice below and fill in if necessary. Fill in the answer box to complete your answers. So this comes from a Math Excel assignment, of course, and it's asking us for the real zeros. And in this case, it's asking us for the zeros at location x equals, and we can list those zeros now. So at x equals -1, -3, and positive 11, that's where we will see our zeros. -3, -1, and positive 11. Now the second half of this question, after we find the zeros, will ask us to use the zeros to factor the function, and all that means is tell us what the factored form of our result would look like. And each of these zeros produces a factor for us, so we can rewrite them again, this time as x plus 3 times x plus 1 times x minus 11. Keeping in mind that any zero, the sign of these zeros is the opposite of what the factor would be. So I think this is a good place to stop the video. We'll continue to practice these problems into next week. So be sure to review this video if some of the parts didn't make sense, and try to practice this particular example on your own. See if you can do it on your own after seeing it done once or twice.